Okay, for our next topic, we'll be discussing operator commutation and the operator version of the Heisenberg uncertainty principle. So first of all, let's define commutation, or start to define commutation. So we've come across this word commutation. Of course, in a legal sense, it could involve reducing someone's sentence, but that's not what we're talking about here. The commutation is related to the commutative property of multiplication. So we know that in multiplication, a times b is equal to b times a. The order in which you place those two numbers doesn't affect the result, right? And we use this commutative property to perform various algebraic rearrangements. And it's something that we rely on. So in quantum mechanics, the algebra is a little different. It turns out that quantum mechanics is essentially a non-commutative algebra. And there's, of course, a similar system in that vector multiplication, matrix multiplication in linear algebra is also not commutative. The order that you multiply matrices in can matter. And that's worth noting because there are some similarities between, that's not the only similarity between quantum mechanics and matrix linear algebra. And in fact, there's a whole branch of quantum mechanics called matrix mechanics that's an alternative formalism that is very helpful for some, very useful for some cases, and we will look into later on in the course. However, so now let's look just at operators as we've defined them so far. Operators, remember, can be things like multiplication, which we expect to commute, but also operators can involve things like differentiation. And differentiation is a very different kind of mathematical operation than multiplication. And we'll see that often operators do not commute, particularly operators that where one of the two operators in question involves a differentiation. Okay, so operators sometimes do not commute. So it's a non-commutative algebra. Which is a label that mathematicians would apply to any sort of algebraic type system where commutation is not one of the properties. Sort of like non-Euclidean geometry, right? It comes up, it's useful in some areas. And anyway, so we say that, so for multiplication, AB equals BA, but the operator version, AB is not necessarily the same as BA. And we can look at this from a mathematical standpoint, but also we can think about it from a physical standpoint. I alluded to the fact in discussing the superposition principle, I alluded to the fact that when we perform a measurement, we sort of force the system into one of the eigenstates of the operator. there's a wave function collapse. And so by measuring, we've actually changed the wave function of the system. So the initial wave function is no longer the wave function of the system. Now, after performing our measurement, we've placed the system in a different state, an eigenstate of that operator, with some probability associated with that. And so since we've caused this wave function collapse, this could affect the outcome of the next measurement. We can think of it as collapse, or just in general, if we don't want to get involved with collapse, which is somewhat of a fraught concept in quantum mechanics, we can just say it changes the wave function. I'll spell it out. Yeah, because you're doing something like, say, taking a derivative, and so you end up with a new function. And so therefore, any subsequent measurements after that initial measurement are going to give you a different answer. So again, this is very different from classical mechanics. Where measuring something doesn't really affect it. You can measure a system without perturbing it in any way. You're just an observer. However, in quantum mechanics, the observer, or the act of observation, or the act of sort of entangling the system that is performing the measurement with the system being measured, this results in some strange outcomes. And so it's different than classical mechanics. So let's talk about how this works mathematically, without worrying too much about the philosophical ramifications. But it's worth maybe pointing out that, yeah, if this seems strange, there's a reason for that. It truly is strange. So some pairs of observables, not all, but some pairs of observables are such that if you measure one, it affects the outcome of the other. And when that happens, those pairs of observables are called complementary. So if we have two kinds of measurements, A and B, and measurement A affects measurement B and vice versa, then we say these are that A and B are complementary. Complementary with a C-O-M-P-L-E-M-E-N-T-A-R-Y, not complementary as in flattering one another. And we say that, so the statement operators corresponding to complementary observables do not commute. Okay, And so this ends up, we can turn this into a test for whether or not two observables are complementary, or if they do commute, we say they are compatible. And this is essentially the Heisenberg uncertainty principle operator version. We'll see how it works in the case of position and momentum momentarily. There are a few different versions of the Heisenberg uncertainty principle, depending on exactly what the question is that you're looking at and what you have, what tools you sort of have at your disposal. This is sort of the operator version. There's another version that has to do with statistics a little bit more directly. Okay, so how do we test we have two operators, A and B, and we want to determine whether or not they commute, whether or not they are complementary observables, or they correspond to complementary observables, or are they compatible? Do they commute or not? So how we test this is, first we define a commutator. Which is another funny sounding word. Sounds like a communist potato or something. All right, so a commutator is defined thusly. First of all, we use this notation of square brackets. Square bracket A comma B, end square bracket, that it represents a commutator for A and B. And its mathematical definition is AB minus BA. And then we can say if the commutator is 0, if it evaluates to 0, and we have to be careful about how we evaluate it. We have to follow certain rules that are not a little bit different than conventional algebra, because again, this is a non-commutative algebra, so we can't just sort of insert commutativity into our system without getting the wrong answer, or risking getting the wrong answer. So we have to be a little careful about how we define things. And hopefully if we are careful and we have some example systems to look at, then we should have a fairly solid tool that we can use to evaluate the commutator and evaluate whether or not two observables, or the operators corresponding to two observables, commute. So if that commutator is 0, then we say that A and B, we say that A and B commute, and therefore we can say that they are compatible. But if we evaluate this difference, AB minus BA, and the result is not 0, then A and B do not commute. And therefore we say that they are complementary observables, that they correspond to complementary observables. So the operators don't commute, so the corresponding observables are complementary, meaning that when you measure one of them, it affects the other one. And ultimately, it ends up being tied to the simpler version of the Heisenberg uncertainty principle, that the uncertainty in, say, position and momentum, the product of those uncertainties, is always greater than or equal to some expression involving Planck's constant. Okay, so let's look at an example. Okay, and we'll see some, you'll have the opportunity in the homework to work through some examples like this. So this could be seen as a guide to homework. So let's look at the case of position and momentum. The x operator is position, the p operator is momentum. You may recall from a few lectures ago. And the x operator is fairly straightforward. It's represented sort of algebraically as just x times whatever's to the right of it. But momentum operator, say momentum along the x-axis, okay, is minus I h bar d dx. Okay, minus I h bar d dx. Or we can forget those funny partial symbols and just say, restrict ourselves to one dimension and say just d dx. Okay, since those are easier to express mathematically. Okay, so now either easier to write, sorry. So let's look at this commutator. So we want to evaluate this commutator, but we need to introduce a dummy function. There has to be something to take the derivative of. Otherwise, the momentum operator is not defined. Okay, so we, without loss of generality, just sort of introduce a dummy function and say we want to evaluate this commutator xp acting on some dummy function. We'll just call it psi of x. And then once we're finished with the evaluation, we can hopefully remove the dummy function, and but only after we perform any derivatives. Okay, we can just sort of divide both sides by the dummy function at that point, and hopefully we aren't dealing with the division by zero problem. We can certainly find a dummy function that doesn't go to zero, so we don't have that problem. We can use an exponential or something. Then let's see what happens when we evaluate this. So this is going to be equal to xp minus px, sorry, and I'm going to drop the x subscript. Well, no, let's keep it. Okay, all of that, sorry, I shouldn't use square brackets, that's a little confusing. We'll use curly brackets. All of that acting on some function psi of x. Okay, now we introduce the algebraic slash calculus, differential calculus versions of our operators. And recall that the operators always act on whatever function is to the right, including other operators. So let's look at that. So let's distribute and replace x and p with their algebraic slash differential version. So that's going to give us x times, and then I'm just going to put in parentheses, minus I h bar d dx, and then we've distributed it over psi. So that's xp, right? This is x, and then the part in parentheses is the p part, minus I h bar d dx x psi. Okay, so that ends up being important, as we'll see momentarily. Okay, so first of all, let's figure out what's happening on the right-hand side. We're going to define psi prime is equal to d psi dx. Okay, so that's just going to be a the notation that we use here. Okay, so then we're going to get, evaluating the first part, we get x times minus I h bar times psi prime, right? The d dx is going to act on the psi to the right, and that's going to give you a psi prime. Okay, for the next one, first of all, let's go and cancel the signs here. So we're going to get plus I h bar d dx, and then that's going to be acting on the product of x and psi. Okay, here we have to be a little careful because this is a product of two functions. Therefore, we have to apply the product rule of differential calculus, which is that d dx of a product of f and g is equal to df dx times g plus dg dx times f, or something equivalent with the things switched around a little bit. But basically you end up with two terms. This ends up having some important consequences because then things are not going to cancel the way we might have initially expected. Okay, so then applying the product rule to that second part. So first of all, let's rearrange the first part a little bit. We'll put our minus I h bar, put that out front, x psi prime, and then we're going to get, looking at our second set of terms, we're going to get an plus I h bar, let's see, dx dx is just 1, so we're going to get 1 times psi plus x times psi prime. Okay, hopefully you see where that comes from, right? We're applying the product rule, differentiating x times psi. So we're going to get psi plus x times psi prime. Okay, then we see a lot of stuff cancels, right? But not everything. And we have to be careful about distributing things properly. And we end up with this minus I h bar x psi prime is going to cancel with this part and this part. Well, part of that. So those two cancel. And we end up with equals I h bar psi. Okay, and I definitely encourage you to follow through this on your own, starting from the same starting point that we used, applying the product rule, and taking you all the way through it. This is a case where just sort of watching it from a distance isn't necessarily going to give you a full feel for how this works. Okay. Now that the dummy function has done its job, we had ended up with some psi primes and so on. The psi prime terms canceled out, and we ended up with just a psi that we started with. And we can remove the dummy function, essentially divide both sides by psi. And we've only really relied on one aspect of psi. One, well, maybe two. One, that it's not zero. And we've all, which of course, yeah, if we have a psi that's equal to zero, then all bets are off, right? The other thing, because you just end up with 0 equals 0. The other thing is that we've used the fact that it has a first derivative. So this is only depending on the notion that the function has to have a value and it has to have a first derivative. Okay, so we have introduced an auxiliary assumption, but these are fairly straightforward assumptions that we would expect all of our real wave functions to follow. Okay, so and we'll see later that in fact one of the rules of quantum mechanics is that wave functions have to be continuous and they have to have a defined first derivative. Okay, so removing the dummy function. And we end up with that the commutator of position and momentum is equal to I h bar. And of course that's for momentum along the same axis. I sort of dropped the subscripts there for the sake of keeping things simple while I was working through the problem. Okay, so this is not 0. And therefore x and p, position momentum, are complementary observables. And perhaps later we'll see how this operator version is equivalent to the initial version of sigma x, sigma p, or delta x, delta p. The product of those two uncertainties is equal to h bar over 2, or is greater than or equal to h bar over 2. That's the sort of algebraic version of the Heisenberg uncertainty principle. So that's just one example. You can look at other problems. What if we were interested in position squared and the commutator with momentum along the x-axis? Okay, because position squared is going to be related to the standard deviation in the position, and so this could be important. We also might be interested in the commutator of x with momentum squared. And we can imagine, so these are other examples, which may show up in the homework or may show up later in the course. These will probably show up in the homework. Later in the course, we may see things like we might be interested in what is the commutator of the angular momentum along the x-axis, commuting with the commutator of angular momentum along the y-axis. Or we might want to know, it turns out this one is not 0. And in fact, it's equal to I, my recollection is, it ends up being IH bar LZ, which is an interesting thing to work through, as we'll see. But it turns out that the L squared operator, where L squared is Lx squared plus Ly squared plus Lz squared, does commute with the Lz operator. And this has some really important implications for quantum mechanics. So, and for handling angular momentum, which shows up in orbitals and in electron spin. So there are just some other examples of commutators that we'll run across in the homework and later in the course. And that's all that I want to say about commutation at this point. Our next subject, commutation and sort of the operator version of the Heisenberg uncertainty principle. The next topic will be the particle, the quantum mechanical particle in a 1D box.